Hi, welcome to module 16. So in this module we are going to look at what the design process for digital circuits are, and I will also introduce you to Verilog. So let us see the basics of a design process. So let us say I want to build a product. So I want to build some product. I start with what are called specifications. I have to say what this product is supposed to do. So that forms specifications. This is also something that you do in software. When you design a piece of software, you say this is what the software will do, these are not the things that it will do, and so on. The same thing is required for doing hardware design. You have to say that this circuit is supposed to implement this functionality, it's supposed to run this fast, these are the conditions under which it should operate, this is the temperature at which it should be able to run. All of these things you design, right? So for example, if you design a cell phone chip, right, if you design a processor for a cell phone, then you have to say that it has to be let us say minus 15 degrees centigrade to 45 degrees centigrade, it should work properly. That is a specification. It has to run at 1 gigahertz, that is a specification. So there are functions that you specify, so you have to specify functionality, what it's supposed to do. You also give performance constraints, you give things like power constraints, it should run within 1 watt, right. So things like that are all constraints. So you start with all this in mind and you come up with a set of specifications. Once you have your specifications in place, you go and do your initial design. This initial design, we have been doing this using Boolean equations and so on directly, right. So you do the initial design, and then once you have your initial design, you go and simulate this. So when I say simulation, what I mean is you need to be able to give inputs to it and find out what the outputs will be without actually realizing the circuit. So that is what simulation means. So see, when you do simulation, you have the design with you, you do not have the final product with you, but when you have the design with you, how do you give inputs to it and how do you find out whether it is correct or not? We will do this in a little while. So we do what is called simulation. When we do simulation, if the design is correct, we can then go and do a prototype implementation, but if the design is not correct, because it is not meeting some of the specifications, we go back and redesign the circuit or the whatever chip that we want. So this simulation is a very interesting thing. So what we are seeing here is what is called the front end design, right. So you start with a circuit, you start with something in mind as a specification, you do an initial design of it. If I do it on paper, right, so let us say I draw diagrams on paper and so on, right, I can only show it to people around me, or maybe I can scan it and send it to you, you can verify it and so on. This is not going to be useful for a computer to be able to take as an input, and we cannot give inputs to it and get the power of the computer to give various inputs and see what the output will be and so on. When we design a circuit using computers, what we want is not just a mechanism by which we can specify what we want, we also want to be able to give inputs to it and see what output it will be. If I do it on a piece of paper, it is not useful because a computer tool cannot take this input and process anything with it, right. So this, what we are going to do in this course is we are going to learn how to do initial design using a language called Verilog. So I already mentioned this in the week 1. Verilog is a hardware description language. We are going to do our design in Verilog, and this Verilog design will be actually a text based description that a computer can process. With appropriate tools, you can actually go and take this Verilog design written as a piece of text, you can give inputs to it, you can find out what the outputs will be and so on, right. All of this you can do, and you can keep doing this till you are comfortable with the fact that the design is correct. So when you do Verilog based design, at the end of what you see in this chart, you will only get a textual description of the design that you want. Once you know that the design is correct on paper, you can do that on paper, but here we are going to use tools to ensure that the design is correct. We write it in Verilog, we use tools to verify whether the description is correct or not. Once you are done with that, then you can go and do your prototype implementation. So till then you do not want to spend money in building prototypes, because prototype means money. You have to buy the components, assemble them, spend time, maybe put them on a breadboard or put them on a PCB, wire them up, solder them, whatever, right, it takes time. You don't want to do this even before you have ensured that your design is correct in, so whatever you have in mind, you have to translate that to a process where you know, where you can give inputs and check whether it's correct or not, right. So this is called front end design, and this process of doing simulation, taking an initial design, writing the design in Verilog, do simulation, finding out whether it's correct or not, and redesign and loop through it if the design is not correct. So this process is called front end design and verification. So you do a front end design using Verilog or VHDL. VHDL is another popular language, and this process is called verification, and verification takes quite a bit of time. So about 60 to 70% of product's time is spent in design and verification. So it's a very important task. Lot of engineers get employed to do verification. So if you go and look at companies in India and worldwide, you will see that most of the design houses have a much larger verification team than a design team. Design teams are smaller, but verification teams are bigger. So there are plenty of job opportunities if you know how to do verification well, design and verification well. So let's continue that process. So at this point in the beginning here, we have a design which we have simulated and verified whether it's correct or not. Now I am ready to do a prototype implementation. So when you do a prototype implementation, you go and test it. If it meets the specifications, then you have a finished product. So you can now sell it to the market. However, if it doesn't meet specifications, you go and see if these are minor errors. If there are minor errors, then you go and make corrections to it and change only the prototype. Maybe there was a manufacturing defect, the design was correct, but the manufacturing was a problem. You were supposed to give a voltage supply of let's say 1.6 volts, you ended up giving a 1.2 volt supply, you have to fix it. So these problems could come anywhere in manufacturing or in the input that you have given. If these are minor errors which can be fixed in the prototype itself, you do that till you are ready and till you can guarantee that the product is actually meeting the specifications. But if you find that it's not a minor error, it's a major error, maybe conceptually you had something wrong, the prototype is actually a faithful replication of your design, but the design itself was wrong. If that happens, you go back and redesign. So this redesign is something that you may have to do, right, in which case if you are redesigning, you come back here and you again do a simulation, find out whether it's correct or not. You keep doing this loop till you are again ready for a prototype implementation. So this process is a very laborious process. So you don't want to really do this cycle too many times. You don't want to go and redesign because your prototype had some, so manufacturing problems are one thing, but if your design is incorrect and if you take it through prototyping, it's a very expensive deal. What you want to do is stay within this as much as possible, check if everything is correct, and once you are sure that this is correct, only then go and do prototype, because prototypes are very expensive. So I am going to show you how to do this process. So the other nice thing about chip design is that this is a one-time affair. Coming up with a design and ensuring that, verifying that this design is correct is a one-time affair. You do prototype implementation, so that you may actually do multiple prototypes and you go and manufacture it, you get it back and you test it. The testing has to be done for each and every chip that you have, but the design and verification is actually done just once in the beginning. Once you have, it's not that for if I make 1 million chips, I have to verify chips 1 million times. The design is verified once, it's manufactured, when you manufacture you get 1 million chips, these 1 million chips have to be tested. So testing is different from verification. Verification is something that you do on with software without necessarily having any chips and so on. You do verification with Verilog code or VHDL. Nowadays we also have system C, system Verilog and so on. But once you have it, you go and do a prototype implementation, you get it manufactured, but once you manufacture it, you have multiple chips, you have to test each one of them to ensure that this can be marketed. I don't want chips which don't work to go to the user. So we would like to get each and every chip tested. So the first part is called front-end design and verification. The second part is called implementation and testing. So what is Verilog? Verilog is a hardware description language, or also called HDL. It's a high level language used to model hardware. I already flashed this slide in week 1. So they have specific hardware related constructs, they can model digital systems and increasingly analog systems and so on also, and they will be extended to system design level. So HDLs, when they started out, they were actually a mechanism by which engineers exchanged their designs. So let us say I as an engineer brought a truth table to do something, and you as an engineer brought a circuit diagram to do the same, do some other functionality, and we have to put this together and finally make a working circuit. I have a truth table, I have to do something, and you have a circuit drawn on paper and pencil. We have to now go through a whole process in which we have to interface and get everything working to design a complete system. So HDLs actually started as a standard for exchange of design ideas. If I write my description in Verilog, you write your description in Verilog, we can take these two descriptions, put them together and make a larger chip. We do not have to translate from one to the other. That is the main intention with which hardware description languages were invented, and it became quite useful after that. So instead of just exchange, people started designing new things using HDLs, and that is what we will do in this course. Let us take a small example. I already showed this example earlier. So what is cool about Verilog or VHDL or any such HDLs is that you type the description and there are tools which can give you the implementation. You write a description like this, and there are tools which will give you what should be the gate equivalents and how they should be connected and so on. And usually you give one description, you can get a variety of implementations. So this arrow mark, there are tools called synthesis tools which will take your Verilog code and generate circuits out of that. These synthesis tools can take the description, they can also take constraints like what kind of gates you are allowed to use and so on. For example, let us say I gave this description and I allowed the synthesis tool to use AND and OR and NOT gate, it may end up with something like this. But if I tell the synthesis tool that you take the description here, however you have to use only NAND gates, then it will give me a circuit in which all these things will essentially be converted to NAND gates. There are tools which can do that called synthesis tools. There are various companies which do this, which develop these tools. So that is a very cool thing to have. You can change the implementation without changing the design that you have. And the other major thing with Verilog is, even though this design is actually written in terms of AND gate, NOT gate and so on, I described this in week 1, you do not have to describe it at this level, you can make it even more abstract. We will see things as we go along, but for this video we are going to see only something which is described in terms of basic gates. So what do we want here? We want to specify a combinational circuit, which means given the inputs we should be able to derive what the outputs are, and at this stage let us assume that we know the gates we want. We have done something in a piece of paper, we have evaluated everything, we have minimized maybe, and we have Boolean equations or even the circuit ready, and I want to represent this in Verilog. So this is not the ideal way in which Verilog should be used, but it is just a logical step from wherever we are right now. So we know how to take a description, we know how to write truth tables, we know how to get basic gates for it. Given the basic gates, how do we write Verilog which will represent the basic gates and the connection? So what we are going to do is, we know the gates that we want to check if the gate level description satisfies the specifications or not. You came up with a circuit, you can write it in Verilog and check whether the circuit is correct or not. Till now we were actually plugging in various zeros and ones and checking. Now you can actually use the power of software and tools and computers to do this. Later in the course what we do is, we may not even know what gates we are supposed to use, we know the functionality, we know what the function is supposed to be, and we will specify it in like a language like C or C++ or something, fairly abstract. We do not know what the exact gates are or not, the logical elements are, and we want to let the tools to figure it out. You can do that also in Verilog. So right now what we are going to do is, we are going to assume that I want to implement a function f in terms of, let us say, 3 inputs A, B and C. We will need a mechanism by which we want to represent the logic which will get f. In this video, this combinational logic is not something which is very abstract, we will describe it in terms of gates, but later we will see how to write it in an abstract way. So let us see Verilog syntax. So you see this thing in the right bottom here, that is the description of a multiplexer done using Verilog. So the first line starts with module, and the last line ends with end module. So whatever you see in red here are actually keywords. Keywords meaning these are words that are used in the language which you cannot use as a variable and so on. So you have module, end module, and in this case we are designing a circuit which is a 2:1 multiplexer. So I am calling that as multiplexer. So module followed by module name, it's multiplexer. And what are the connections to a multiplexer? There must be 3 inputs, A, B and select line, that's a 2:1 mux, and there is one output called out. So there are 4 pins. If you buy a 2:1 mux, you will see 4 pins for the data, and maybe you will see power pins also, right? So we are not showing the power pins explicitly here, it's not necessary. We will only show the data input and output connection. And what you see here are called ports. So ports are, you have a circuit, what are the inputs and what are the outputs to it, right? Pins may include all your power supply, clock, whatever, right? Whereas ports are, what are the inputs to this design and what is the output from the design. So we have 4 ports, namely A, B, select and output. And if I tell you this as the 4 ports, there is no, Verilog by itself does not know what is input and what is output. Verilog does not know what multiplexer is. You have to explicitly say which are the inputs and which are the outputs. So in this case, A, B and select SEL are inputs. So we indicate that by saying input A, B, cell, and we want out to be the output port, we explicitly say output out, right? So far it's all clear. Then what did we want? We want to, let's say we want to implement this circuit here. We need 2 AND gates, 1 OR gate, 1 inverter. We also need all these wires to connect intermediate ones. For example, there is a wire that is coming out of here, and there are 2 wires that are coming out of the AND gate which should go to the input of the OR gate. We need all of these connections, right? So to do that, we need 3 wires. There are 2 wires, temp 1 and temp naught, and 1 wire called select bar, which is going to be complement of select. So this is something I showed in video in week 1 itself. So AND temp 1 B cell, right? This line is saying I want an AND gate which will take B and select as inputs and which will produce temp 1 as output. So if I think of it as a physical circuit, I am picking an AND gate, and to its inputs I am giving B and select, its output is called temp 1. Similarly, not of select is select bar, and of A and select bar is temp 0, and OR of temp 0 and temp 1 is out. That is what this description says. So in this description we also have AND, NOT, AND and OR here. These are marked in red, they are also keywords. They are called Verilog primitives. So these primitives are therefore Boolean functions, basic Boolean functions to be used directly. So in this case, this primitive takes 2 inputs and 1 output. So remember, all the primitives are only 1 output functions, AND, OR, NOT, XOR, all of these are actually just single output, right? So the first thing will be for the output and rest of them will be for input. So and this one will imply that you have an AND gate with temp 1 as the output, B and select as input. This one is OR, has out as the output and temp 0 and temp 1 as the inputs. All the internal nodes are declared as wires. So the second line, the second set of lines is inputs and outputs. Then you have the design description given here followed by end module. So this is a very simplified version of Verilog syntax. So now I am going to take a specific example and write Verilog code for you. So let us take this example. So what we are having is, let us assume that there is a hospital in which there is medical waste. So it could be tissue, it could be the gauze that they use, or cloth that they use, or scrubs or whatever, right? So all these are toxic. You don't want this to go to the environment directly. So typically what hospitals do is they take the input and they burn, they take all these things and burn them. So anything that's coming out of a surgery, right? So they may remove tissue, but in the process doctors may have used gloves and whatnot. They take all of that and send it to an incinerator. The incinerator is supposed to take them and burn them, and that is now safe for taking out to the environment. Otherwise you may have all the bacteria and viri that may go out to the environment. You don't want that. So let's say you take this toxic waste as an inlet, and there is a valve which controls the toxic waste. what we are going to do is we are going to bring the waste into a chamber and we are going to inject fuel into it, and the fuel is supposed to burn the toxic inputs, toxic waste. So let us assume that the fuel can actually burn everything down and send it out. When we send it out, let us assume that the output gets sterilized, right. So the issue is we are having a fuel injection, so there are various things that can happen. So the fuel itself gets over. If the fuel gets over, you do not want to keep pumping more and more inputs, because the input may go without getting burnt, it may go to the output, you do not want that. So what we want is, we want to have a mechanism by which we have to continuously monitor whether there is a flame, and for whatever reason if the flame is not there, we want to immediately shut off this valve so that no more inputs are taken, and we need to go and fix this setup before which we can start operating this one. So to do this, just like in one of the earlier examples I showed, I am going to put various sensors. Let us assume that I put 3 sensors A, B and C. The job of this sensor is to figure out if the flame is there or not. So again, like I said, the flames could go off due to various reasons. Maybe there is no fuel, or there was a power cut, it could be various things. So you do not want a mechanical valve to continuously dump this medical waste without checking what is happening with in this incineration chamber. So I am going to put three sensors A, B and C. They are going to verify whether there is a flame or not. As long as there is a flame, as long as there is a flame, things will get burnt and the valve can remain open. But if there is no flame, then I want to shut off this valve. Right? To do that, I want a Boolean circuit or I want a digital circuit. So we want to put a logic system that will shut off the waste valve if no flame is detected. Right? So this is a simple description problem. Right? So this design problem is interesting because we can show various interesting aspects with it. So let us see this. What can happen is, these 3 sensors, if they are always working, right, and if there is a flame, they will give 111 as their output. They will say that the flame is there. If the flame is not there and if the sensors are always working, you will have 000 as the output. However, what can happen is, these sensors themselves may go bad. Right? The sensors are also subject to failure. Maybe this sensor was replaced 5 months ago. These 2 are new sensors. So eventually the sensor fails. I may have to replace its battery, or I may have to replace the sensor itself. It could be any of those. So if I want something like that, then it is possible that you have 3 sensors, but some of them are failing. We want to build a logic system in such a way that even if there is something which is failing, I do not want the exhaust to ever have toxic waste automatically go in. Right? In the worst case, I have to shut it down and I have to be careful about this. So to do this, right, one way in which you can achieve this is use what is called the majority function. I already talked about this in the previous module. So if the majority of the sensors detect the flame, then open the valve or close the valve. This is a very safe way in which you can operate it. Right? So it is not that you are looking for all 3 of them to tell you that there is a flame. Right? If there is a flame, if all the sensors are working all the time, then it is simple to say I will go and look at all the sensors. If all of them are 1, then it is okay. Right? But what can happen is, some sensors, we know that some sensors will fail. So if the sensors A, B and C give 1, 0 and 1 as output, A and B are sensing a flame, A and C are sensing a flame, B is however not sensing a flame, what do we do now? So what we want to be able to do is to look at something like this. If the majority of the sensors detect the flame, then open the valve, because it is possible that some sensors have failed and they are not detecting any flame at all, else close the valve. So we are assuming that the valves, when they fail, they will always say that the flame is not there. So it's, we do not have a condition where something fails and by mistake it detects a flame. Let us assume that we do not have a sensor like that. The sensors, if there is no flame, they will say no flame. If there is a flame, they will say there is a flame. However, when the sensors go bad, it will give you only one thing saying that the flame is not there. It will not by mistake say the flame is there. Let us say if that is the case, then the majority function will do that. So if I look at the 3 inputs, all the 3 sensors say that there is no flame, then I can conclude the conclusion that there is no flame. I have to shut off the valve. If all of them say 1, then the majority of them is saying a 1 because all of them are saying a 1. So it is 1. Look at the other entries. Let us look at this entry for example 0, 1, 0. 2 sensors are not detecting the flame, 1 sensor is detecting the flame, which means there is something wrong in this system. There are 2 sensors which are not detecting, 1 sensor is detecting. So we do not know whether there is a flame or not, but the majority says there is no flame. So we will say that there is no flame. Similarly, if 2 of them say there is a flame and 1 of them says there is no flame, the majority says there is a flame, so we will use 1. So that is the truth table. Written as a corner map, you have this entry. So you know how to write it, I will not go into the details now. Now I want to map these things. So to map, there are 3 groupings of 1 that are possible. So a vertical group of 1, these 2 can be grouped together and these 2 can be grouped together, and I can go and write it as a Boolean function. So f equals AB plus BC plus CA is the Boolean function. This takes the majority of the inputs. You can see it here. If either AB or BC or CA is 1, right, immediately you can say f is 1, right, otherwise you have to look for the other variables also. So this is the Boolean function for a majority 3. So this is a majority of 3 inputs. This is useful in various cases. So let us say 3 of you want to, so you and your 2 friends want to go and have dinner, right, and you are deciding whether you want to go and have pizza or whether you want to go and have let us say a regular meal somewhere else, right. You want to take a vote, right. So you can take a vote and say whoever is the majority wins it. So this is also something that can be captured by this function. So you take individual votes and you combine it using this AB plus BC plus CA, the majority function will tell you what the majority of you have decided. Of course all of you may decide you want to go and have pizza, or all of you may decide you want to go to some other restaurant. So that is the use for a majority function. Now I want to go and do this in terms of Verilog. So I want to design a majority 3 circuit. So it is a single output bit. This output bit will control whether the valve is shut off or not. If the valve, if f is 1, right, then there is flame, you do not have to shut off the valve. If f is 0, then we are the vote is flame is off, so we will go and shut off the valve. So we need a logic description. This has 3 input ports and 1 output port. We still need combinational logic here, right. We already know that AB plus BC plus CA, we will need 2 input AND gates and 1 3 input OR gate. So we need that. Let's see how to write this in Verilog. So the first line I am going to write is keyword module, and I am going to give a name to the circuit. So any circuit that is designed, you have to give a name in Verilog, it is compulsory. It can be any name that you come up with. So I am now calling this circuit as MAJ3. This stands for majority 3. Majority 3 has 4 ports, out, A, B and C. They are all comma separated. At the end of this you see a semicolon. This is the interface description of this module. As I said earlier, just the interface description is not enough. These are input or output ports, right. We have to say whether these are input or output ports. So in this case A, B and C are input ports and out is an output port. So that's explicitly described in the lines below that. So we only say that there are 4 ports outside, and in these 2 lines we declare whether they are input or output. In this example there are 3 inputs and 1 output, and I am also going to follow the convention whenever possible to have the outputs before the list of inputs. So in this case it is a single output, I will put it at the front and all the other things are inputs here. So if I have more than 1 output, I will pick some ordering of the outputs, I will put them first and then I will put the inputs. There is a reason why I do that, I will come to that later, right. Then we needed 3 intermediate nodes. So AB gate will, so the gate which does AB will need a wire, the gate which does BC will need a wire, and the gate which does CA will need a wire. So we need 3 wires AB, BC and CA, right. So these are the intermediate nodes, and now I am ready to do how to get these individual components. So how do I get AB? AB should be the AND of A and B. So what this is actually saying is, I am going to pick an AND gate, and to this AND gate I am going to give one of the inputs as A, one of the inputs as B, and the output from the AND gate I can put a wire and say I am going to call this AB. This is what you would do if you do this in a breadboard, right? You would go and pick a AND gate and you will put it on the breadboard. You will connect two inputs A and B to it, and wherever the output pin is, you will take that and you will keep it dangling for a while. So you know you want to use this later, you will keep it dangling. Then similarly you need logical AND of B and C as well as A and C. Now there are 3 AND gates and the 3 output wires are dangling. So remember, wires are bidirectional, there is nothing. So if you pick a wire, you cannot say this is the input and this is the output, correct? So wires are bidirectional. The same applies to wires in Verilog also. So there are 3 inputs A, B, C and 1 output out. These are also wires, and then you have wires AB, BC and CA, which are all intermediate wires that you need. So you have picked 3 AND gates and you have 3 dangling wires now. They are called AB, BC and CA. They form the one end of the wire. The other end of the wire must go to the 3 input OR gate. So this OR out comma AB, AC, BC is essentially doing this. So this OR is a primitive, there is one output, rest of it is input. So look at the AND gate, it's one output, 2 of them are inputs. In this OR gate there is one output and 3 of them are inputs. So since all the primitives are single output function, the first one is always an output, the rest are inputs. It can be 2 input, 3 input, 4 input, 5 input, it can be any number of inputs for the primitives. In this case I have used 3 2 input AND gates and I want to use a one single 3 input OR gate. So this implies that there is a 3 input OR gate, this is the output called out and these are the 3 inputs that are coming into the gate. So this gives us the description that I will take A, B and C, I will give them to the 3 gates A, B, B, C, C, A, there will be 3 wires that will come out of it. These 3 wires will go to the 3 input OR gate which gives you the output. We are done with the description of the circuit. So the last line is end module, which finishes the description of the module. So you can see that by looking at this, you can actually go and draw a circuit. If I gave you this without telling you what the circuit is, if I gave you a Verilog description, everything that you need to get a circuit is there. So if I gave you only this, you can see that, oh, I am designing a black box which has 1 output and 3 inputs. In this black box, the 3 inputs are called ABC and the output is called out. I will need 3 more wires inside and I will need 4 gates of this kind, and this tells you this is the connection that you need, right. So all of that is there, anything that you need to describe the circuit is there. So given a Verilog description, you can draw a circuit. We started the other way around. I gave you the circuit and I wrote Verilog because we don't know Verilog yet, but given Verilog later, you may be able to understand what the circuit is by just looking at it. Now let us say we have designed a circuit to do this. How would you test it in the lab? In the lab, you will put it inside what is called a test bench. So what you will do is this, you will probably pick up a breadboard, you will put all these components and so on, connect them, you have the design ready. And once you have it ready, you want to check whether it is correct or not. Maybe your teacher wants to evaluate you, you want to check yourself whether the circuit is correct or not before getting it evaluated. What will you do? You will go and connect the input wires that are there, maybe to VDD or ground to decide whether it is 0 or 1, and at the output you may either connect it to an oscilloscope or you may connect an LED and see whether it glows or not and so on, right. That is a test bench. What you have is you have a bench in some sense in which you put your design, you are able to give inputs to it by connecting to power supplies, you are able to take the output and see what the output is, either by looking at the oscilloscope to which you have connected or by looking at LEDs or something like that to which you have connected. It could also be something like I will go and drive a motor, the motor should run. It could be any of those, right. So you need a test bed in which you can check this. So we are going to call that a test bench. A test bench is going to take the device under test or DUT. So the device under test in this example is majority 3, MAJ3, and what I am going to do is I am going to instantiate, I want to have one copy of this circuit to test it, right. If I want to check whether it works or not, I want to take that one copy of the circuit, which we are going to call instantiation. We instantiate it, we need a mechanism by which we can give test inputs to it, and we need a mechanism by which we can observe the outputs. So from a software angle, in some sense, you need to be able to take inputs to a program and outputs from the program, right. Typically what you do is you go and type the inputs in the keyboard, or you go and type, you give a file as an input and so on, and the outputs could be something on a screen or something on the something in a file. We need something like that for hardware description languages. We need to be able to give inputs and we need to be able to observe the outputs. So the outputs could be in terms of a file that gets printed or something that is printed on the screen or something you can see like a waveform, and the inputs could be a mechanism by which you can give specific inputs in some order. So in a real circuit you may actually connect switches, a dip switch to connect from 0 to 1 or so on, but if you are going to write Verilog, we need to write the whole thing inside Verilog. So in Verilog what we are going to do is we are going to design a Verilog module called a test bench. This test bench is going to instantiate a module called device under test, and in the test bench we will have mechanisms to provide it inputs and see the outputs or capture the outputs. We will see how to do that. So what the usual practice is, the design that we have, we are going to write that in a file which ends with a .v. In this example, the device under test is a majority 3 function, the module name is maj3, I am going to call that maj3.v, and the whole design itself, the test bench for it, I am going to write it in a file called majority3_tb. This tb will stand for test bench. So maj3_tb.v is the test bench for it. So the test bench, if you look at it, it's not taking any external inputs, it's not giving any external outputs. It is generating all the signals that is needed for the device to be tested, and whatever is coming out of the output, we are supposed to capture it somehow. The test bench itself is not taking any external inputs, nor is it giving any external output, right. So we will have to capture this in our description also. So what I am going to show is how to write the Verilog code and how to write the test bench for it in the next module. So the Verilog test benches are also written in Verilog. Test benches will have no input ports or output ports, and it should have the following mechanisms. You should know what design you are testing, you should know how many inputs and outputs are there, you should be able to change the combinations of inputs to test the design under test, and finally be able to observe the outputs. These are all the different things that you need. So the next module is actually a demo of how to do this. So just go back and look at the slides so far in this module, absorb the finer details of the module, right. Go and look at inputs, outputs and all these other things. Watch this video maybe one more time if you want to know what the different keywords and other things that we have used so far are. So in the next module I am going to show you a demo of this majority 3 function, and we are going to do this online, and this is exactly what you will do for your homeworks and other things later. So thank you very much.